Okay, just like we did with the squares, we also do with the cubes. So here we have 2 cubed, right? 2 times 2 times 2, or 2 times 2 times 2 uh, is 8, right? We have 8 cubes in this 2 by 2 by 2 cube. 4 here and 4 down there. Here we have 3 by 3, so there's 9 on the top face and then 3 layers, so 9 times 3 is 27. So 2 cubed is 8 and 3 cubed is 27. So what happens if we have a side length that is not 2 or 3, between 2 and 3, right? So 2.5 cubed. So what do we end up with there? So we multiply 2.5 times itself 3 times, and we get 15.625. So if I added up all the cubes, that would be in this shape, including all the little fractions of a cube. So if this was 2.5, so this length here is 2.5, and over here we have half and then 2, and then over here it's half and then 2, and 2.5. So kind of the backside there is a half, and this is a half. So the number of cubes in this right here would be kind of a half of a cube, because it would be cut in half on both ways. So I'd have to add up all the little partial cubes and everything like that. And if I add up all the little partial cubes, I would end up with 15.625, which 625 is 5/8, I think. So 15 and 5/8 of a cube would be the total number of cubes in that type of cube. Now, what if I was given the number of cubes and then I wanted to find the side length? So that's undoing this cube idea. So if I was given 27 and I wanted to find out the side length, I would take what's called the cube root. So the cube root has this little thing called an index right here in the corner, and we make it a 3. Now we do so many square roots that we don't even write the index, but if you wanted to do the square root of 16, for example, is 4, there is sort of an index there that it's a 2. It's kind of undoing the square. So that is not actually shown typically because we do it so many times. So the index for square root is 2 and the index for cube root is 3. And if you want to do the 4th root and the 5th root, that would change, but these are the ones that we use the most, is the square root and the cube root. So what number, and root, by the way, root means what? With a tree, right? Tree roots are what are built up from, right? What the tree gets built up from. So what do we build up from to get this 27? Well, it takes 3 3s together, 3 cubed, to get that 27. So the cube root of 27 is 3. And if we were given some other number that wasn't a perfect cube, so something like between 8 and 27, so like the cube root of 20, we could say, well, that cube root of 20 is between 3 and 2, right? Because the cube root of 27 is 3 and the cube root of 8 is 2. So I know that is between. So that's how you can place those on the number line. And I know that 0, 1, 2, 3, that this is 2 and this is 3. I can place the cube root of 20 between those two numbers. While we're here talking about cube roots, I thought I'd share this interesting story. This guy right here, Ramanujan, he was a genius from India that was discovered by the English mathematician G.H. Hardy from Cambridge, and he came over to England and studied there in Cambridge, and later in his life, which was a short life, I think he only lived to 35 or so, but he got sick, and when he was in the hospital, G.H. Hardy came to visit him, and to cheer him up, he decided, hey, let's talk about some numbers. And he said, oh, the cab that I rode in on had the number 1729. That's just such a boring number. And then Ramanujan responded, oh, no, 1729 is very interesting. It's the first number that is the sum of two cubes in two different ways. So it's like, you have two cubes, x cubed plus y cubed equals some number. And he said 1729 is the first number that's the sum of two cubes in two different ways. And you can see them here that, 9 cubed plus 10 cubed is 1,000 plus 729. Right? So 1,000 plus 729 is 1729. And then also you see here 12 is 1728. So 12 cubed plus 1 cubed, 1 is 1. So this is 1728 plus 1, which is also 1729. So I just thought that was interesting. I'm sure it wasn't his most amazing mathematical discovery, but it's one of the legends that lives on.